Hey, it's me, Sam. Today I'm going to talk about my temperature controlled fan circuit. And this video is going to show you this actual circuit. I'm going to tell you what it is, how it works, and the design process that went into actually making the circuit. And I'll tell you about some problems I ran into along the way building it. And I'll have a video of it actually in action. So I'm going to go ahead and start with what I designed first, which was the sensor circuit, which was pretty easy to design. So we were given the equation for resistance of a thermistor, which equaled, so I'll just write R of T equals 5 kiloohms minus 0.025 times the temperature in degrees Celsius. So that correlates an increase in temperature, with a decrease in resistance. And a decrease in resistance, if we were to output our sensor circuit, have the output over the thermistor, we would have a decrease in voltage correlated with an increase in temperature, which is kind of confusing. We want an increase in voltage, or an increase in temperature correlated with an increase in voltage. So what I did for that was I had my potentiometer, and I had another resistor, just a fixed resistor, let's say R1, and we have RT here. And we're going to have the output there, let's say VN right here. And then we have ground. So this is our output right here. I'm just trying to make sure I'm not talking too loud. So this is our output here. And when the temperature goes up, the resistance of this goes down. So using the voltage divider rule, the voltage across R1 goes up. So a decrease in temperature will give us an increase in the output of our sensor circuit. So let's see. And I needed to find a good value for R1. So I wrote out, let's see, plus minus V naught. V naught equals Vn times R1 over R1 plus RT. And let's see, RT, and I lost my calculator. Be right back. Erase all this. So I know that I wanted my Vn to be 12 volts because I knew we were operating a fan here, and I thought that computer fans take 12 volts to operate. And a lot of other people chose, I think, like 6 volts or something like that. But I wasn't aware of that was going to be the standard when I chose mine. I think I did it before the lab, so I just chose 12 volts. Let's say we know RT at 30 degrees equals 5, got all kinds of crazy stuff going on my calculator. 5 minus 0.025 times 30, so 4.25, almost wrote pi, ohms. RT at 100 degrees equals 5 minus 0.025 times 100, probably do that in my head, 2.5 ohms, or sorry, kiloohms. So we're going to go ahead and write our voltage divider here. V naught equals R1 over R1 plus RT. So V naught at, let's say 30 degrees times Vn. And then we have V naught at 100 degrees equals R1. Oh, I put R2 here. It'll be 12 R1 plus RT at 30 degrees, which we know to be 4.25. And then R1 over R1 plus 2.5 times 12. So what I did was, to find the value of R1, instead of just choosing it arbitrarily, which I thought, well, let's find the maximum hysteresis. So that would be V naught at 100 minus V naught minus 30 equals, like H. And then I found H prime and found the value for R1 that would equal 0 for H prime. And that gave me a value of, I think, 3.26 kiloohms. And I ended up using 3.3, which is like very close. I don't think that was really necessary. I probably could have just chosen something in that realm and been fine. I thought, that would eliminate chatter to a higher degree, but it probably wasn't necessary. So the next thing in the circuit is the Schmitt trigger, and the requirements for the fan circuit was for the fan to be on or to be off when the temperature is less than or equal to 30 degrees, and for the temperature to be on when it is greater than or equal to 100 degrees. And what a normal op amp would do is we would have, let's say, plus and minus here, and let's say we have our reference voltage and our input voltage. So let's say the reference is 5 volts. So what would happen here is, let's say 5 volts was the output of the sensor circuit when it's 100 degrees. So when the input reaches 100 degrees and it outputs 5 volts, the fan would turn on. But the thing is, if it dropped to 99 and fluctuated around there, it would output on and off and on and off and on and off like that. So what the Schmitt trigger does is it will have 2 thresholds, one for the rising edge and one for the falling edge of the signal. So let's say we have a signal like this, right? And here is 30 degrees, and here is 100 degrees. These are 2 voltage thresholds. The voltage threshold low, and then the high threshold. And so for the rising edge, which is right here, it is the output is low when it passes the low threshold, but once it passes the high threshold on the rising edge, the output is high, and then it doesn't turn off until we reach the low threshold here. But mine, okay. Mine was actually an inverter. So an inverter op amp. So when it reaches the high it starts off high, and then it reaches the high threshold here. It shuts off, and then when it reaches the low threshold, it turns back on. And that's not what we want. So to reverse this, I just use another op amp in addition to my Schmitt trigger to reverse that. So another consideration was the type of op amp, or the type of Schmitt trigger that I wanted to use. And there were a couple types. Let's see, the inverting Schmitt trigger. However, the threshold values for these, one is negative and one is positive. And I didn't want to do that because I knew that my lowest output of the sensor circuit would be somewhere around like 2 volts. It wouldn't be 0. and my highest output would be 12. So I knew I wanted it in all my threshold values to be positive. So I had to choose, let's see, I needed to choose the single supply inverting Schmidt trigger with offset. And the diagram is shown on the screen. All right, so I'm going to briefly explain how one of the Schmidt triggers works. Not the one that I ended up using. I actually didn't do all the math to figure out how it works. I just used the textbook that was provided by our professor to find our values for R1. But just to show you how it works, here's a Schmidt trigger, and this doesn't have the voltage offset that the other one for the thresholds. This has voltage thresholds that are in, on both sides of the x-axis, so negative and positive. So for this Schmidt trigger right here to switch, we know that VA needs to equal to 0 volts, and V out, I'm just going to put V naught, will be equal to plus or minus 12 volts. So at plus or minus 12 volts, we need to find out what V in needs to be for VA to be 0. So if this is 0 right here, that's ground, right? I think it's like a virtual ground or something like that. I'm not really sure. So we know that our currents are running like this. So V in over R1 equals V naught over R2. So V in equals R1 over R2 V naught. So we know V naught is going to be plus or minus 12. And let's just say R1 equals 1 kilo ohm, R2 equals 2 kilo ohms. So that's going to equal V in, these are our thresholds here, plus or minus 6 volts. So that's pretty simple. So the design of the Schmidt trigger I did was actually pretty simple. There are a bunch of criteria and equations given to us by a professor in this unknown textbook. I tried to find the name of it. But I basically plugged in all my threshold voltages and solved for the various resistances necessary to have those threshold voltages in the Schmidt trigger. And yeah, it was pretty simple. The next thing I did was go into Multisim and just design my circuit, and then I put an inverter on the output of the Schmidt trigger so when the output of the Schmidt trigger was low, the output of for the fan is high, and vice versa. So yeah, so the next part of the video, I'm going to show, my actual circuit that I constructed, the actual thing here. So let's get a little close up. So here is my potentiometer, which is simulating the thermistor, and that is connected to the positive rail, and then we have our fixed resistor R2, which is 3.3 kilo ohms, I think, and that goes to ground. And then we have that red wire right there. I know there's a couple, but the one plugged in there outputs into the inverting pin of the Schmidt trigger. And let's see, there's just wires aplenty here. Let's see, the positive input Let's see, what color is that? That's that white wire right there. That has a couple options. It connects to, let's see if I can get this to focus, to R1 and R2 according to the diagram our professor provided us with. One of those goes to the positive rail, the other one to the ground. And then at that junction, we also have the output of the Schmitt trigger, which is that other white wire in the midst of things. And between that and the junction, there's R3. And then the output of the Schmitt trigger also goes to, let's see, that red wire to the negative input of our inverting op amp here. And let's see. All right, so the last part of the circuit here is the inverter. And we have VCC negative connected to ground, VCC positive connected to the plus 12 volts. We have the positive input connected to the ground and the negative input connected to the output of the Schmitt trigger. And then the output over here between these two diodes, so that when the output is 12 volts, the potential difference across the red diode should be 0, and across the green diode it should be 12, and vice versa. But the output is actually 2 volts, I think, the low output. So the green diode will somewhat be on, and the high output is, I think it was somewhere around 11, so the red might come on. And then let's see, yeah, so I had a problem with this in Multisim. I don't know, with another op amp besides the 741 in Multisim, I had the positive input on the op amp connected to 0, and the output of the Schmitt trigger was negative, so it would actually output high when the voltage was low. But in Multisim using the 741, the lowest output was 2 volts, so it never dropped below 0 to give us a high output in Multisim. So in Multisim, I ended up actually, let's see, using a voltage divider to fix that. So I used the voltage divider to set the reference to 2.2 volts fixed, or around 2 volts. So when it was less than 2 volts, the output would be high, and when the output was high, greater than 2 volts, the output was low. Yeah, but it shouldn't work like this, I don't think, because I don't have that voltage divider here. The positive voltage reference is connected to ground, and it never goes below 0 volts. So I'm not sure why it works, but it does. So I wouldn't dare mess with it. I've already had it assessed by my professor, so there's really no sense in changing it now. It works. So here's a video of it in operation. So I hope you enjoyed watching. That's it for the video. I know in the last clip it was kind of hard to see which LED was on, and also the green was a little bit brighter than the other, and I couldn't really figure that out yesterday in the lab. I spent a while trying to figure out what was wrong. I'm not sure if there is anything wrong, actually. The LEDs were brighter viewing from above, and my professor also told me to use a higher resistance on the LEDs since I was using a higher voltage than everyone else. and that helped a bit. So I hope you guys enjoyed watching. I had a lot of fun making this.